Hello, everyone. Today is the 6th of August, 2023. Welcome to BayesStream number one. My name is Jakub, and today we're going to be talking about active inference. I'll be giving a very brief introduction to what active inference is and how we can think about it in the broader context of deep learning and artificial intelligence. So this is a one-slide overview of active inference. Active inference is a framework for modeling, both theoretically and computationally, any system that can be said to persist through time in its environment. And the theme of persistence is particularly important due to its relation to the free energy principle, about which we might talk about in another live stream in the future. In active inference, perception and action are essentially a means for uncertainty minimization, and uncertainty is usually cast through the lens of variational free energy. The theoretical formalism of self-organization, which underwrites a lot of the active inference literature, uh, itself follows from the free energy principle, which has been applied in various contexts, not only active inference, but also Bayesian mechanics, which deals with a free energy interpretation of classical mechanics, as well as the holographic principle, which casts the free energy principle within the context of quantum information theory. Within the context of computational modeling, active inference agents are performing approximate Bayesian inference on their sensory outcomes and are building an internal model, generative model of their environment and trying to minimize their uncertainty to reach a preferred state. Why do we need active inference? Well, in essence, understanding complex systems is akin to understanding ourselves, societal organization, and any other things with similar properties. So we want some kind of formalism to understand how different things are related, and active inference, as well as the free energy principle, gives us the tools to understand systems at many different spatiotemporal scales with the same unifying language. I would also argue that understanding is a prerequisite to innovation. So, for instance, if we want to create new types of persistent systems, which may include AI, but it may also include different types of societal organizations, both local and global, we have to first reach this unified understanding of how these systems behave and what are the similarities between them. On the theoretical front, there have been many exciting developments in both quantum information theory and classical physics. Well, active inference and its formalism applied within these contexts, as well as many other developments that I'm not mentioning on the slide, such including, for instance, category theory, as well as synthesis between predictive coding or current deep learning methods and active inference. Some of the key challenges that I'd like to note at this slide are scaling computational models beyond simple examples and a more thorough synthesis with deep learning approaches. And this is supposed to be both on the computational side with actual usable examples and tools, as well as on the theoretical side, so that the language used in deep learning research is more compatible with the language used in active inference research and vice versa, so that more collaboration and communication can happen between these two areas. Next is validation with real-world data. In much of active inference research, we are focusing on or appealing to biologically inspired formalism and formalism that is supposed to model real systems. Nevertheless, a lot of the work has so far been theoretical, and this is also related to the scalability of these computational models. And I think these 2 points are going to reinforce each other in the future. So as we scale our computational models, we are able to model more complex systems and hence validate our models with existing real-world data. As with any other field, including deep learning, the key challenge is always asking the right questions and identifying the right problems to tackle. Um, so identifying which problems uh, represent the low-hanging fruit in terms of being us being able to model them with probabilistic approaches as opposed to deep neural network models, and building easier to use tools. Again, this is more on the onboarding side and being able to communicate across different communities and enabling more people to test out the formalism and play around with it. Here is a hint at an intuition that I'd like to communicate, comparing broader artificial intelligence with active inference. So there's a famous quote that um, is often found in introductory deep learning courses by Pamela McCorduck. And it says, artificial intelligence began with the ancient wish to forge the gods. I would offer a similar quote for active inference, where active inference began with the ancient wish to understand systems that persist. I'll let you decide what the similarity and differences between these two sentences are. Of course, it's also partly meant as a joke. Nevertheless, I do believe that it's important to draw these parallels between different scientific fields to understand the motivation behind why we're exploring particular topics. Now, this is the second time that I mentioned systems that persist. So it'd be good to elaborate what exactly we mean by that. Systems that persist can be both biological and non-biological. And the free energy principle and active inference can, in essence, be used to analyze both and model both, although uh, depending on our own internal preferences, we might want to model particular systems more than others and use different formalisms to model different kinds of particular systems. But here are some examples of systems that persist. For instance, a tree, a rock, the rock, a galaxy, a cell, or the United States, or the states within the United States. And this is hinting at the multi-scale affordance that the free energy principle provides for modeling nested systems where there is a particular boundary that distinguishes systems at each level of organization. Here's a one-slide comparison of active AI and active inference. And in this case, we're only focusing on discrete models in active inference, and this list is by no means exhaustive. And it is definitely a coarse graining of the possible comparison that we could do if we wanted to go in a bit more detail. So, in essence, deep learning models get useful patterns from data to automate a subset of human decision making. In contrast, active inference in discrete state spaces models how systems act in their environment to persist through time. And this is enabled by both the process of perception and belief updating, as well as action and adapting the environment to fit our preferred observations. Deep learning is usually deep learning models are usually trained on data and then used for inference. And once they're trained, uh, they usually don't change their structure very much. And the inference in this case can be thought of as fixed. On the other hand, active inference models are trained during execution, if we can call the process of uncertainty minimization training. This is usually done in test environments, and this again appeals to the problem of scalability. And then they have previously been used to identify salient dynamics of the systems of interest. Now, this can be in cognitive science, where you want to identify the uh, the particular cognitive states that an agent reaches in their environment, or anything else. Currently, I think it's safe to say that deep learning models have mostly been used more of more as an API than as autonomous agents. When deep learning models are deployed in autonomous systems, usually there are some other components that form the autonomous part, and deep learning models are mostly used for the um, inference part, where there is some system that draws information from these models. On the other hand, active inference is currently used more like reinforcement learning, and in um, in many recent works, it has actually been called a generalization of reinforcement learning, because unlike in reinforcement learning where there's an explicit value function or even an implicit one, but a value function nonetheless, um, and the agent is always optimizing for reward, in active inference there is no value function, or rather the agent is only acting so as to minimize its uncertainty over its sensory input. So the goal is not to reach a particular state that will give us the most reward, but the goal is to reach states that are the least surprising and in which we have the most agency. The last 2 points are for deep learning models, they have in recent years become more scalable, um, particularly some architectures have become more scalable than others. Um, and they scale to many applications, but they do require um, a lot of human intervention to figure out their particular architecture. Active inference currently faces issues with scalability, um, and the question of architecture is definitely also present in active inference, because beliefs are usually explicitly defined in active inference models, as opposed to deep learning models where beliefs are more distributed across many different nodes and um, are not as readable as probabilistic models in active inference. And this is the last point, where deep learning models are usually treated as a black box, where explainability is very hard in terms of identifying why certain properties of deep learning models emerge after training. And we can also argue that innovation in deep learning is largely driven by experiment rather than first principles, although there's definitely some first principles thinking present in deep learning models. On the other hand, active inference is probably slightly more grounded in first principles, particularly because it's mostly derived from the free energy principle. So the word principle is already there in the title. And they are not a black box in the sense that probabilistic beliefs are explicitly encoded within the generative models. And it's much easier, or not necessarily easier, but it's, well, for the purposes of this introduction, let's say it's easier to identify why that an agent believes a particular um, transition between states has a particular probability, or a particular observation is mapped with a certain level of certainty to a particular state. So both beliefs and, as a result, uncertainty about those beliefs is explicitly encoded in active inference models. But that doesn't mean that active inference models cannot, in the future, be also developed with a black box architecture. But at least the current state of active inference literature mostly focuses on models which are not. To conclude this short introduction, let's comment on the theoretical value of active inference. As I already mentioned at the start, one of the biggest advantages or potential utilities of active inference is that it provides a shared language that everybody can understand and that is consistent across different disciplines. So active inference can be applied to both psychology as well as AI. Now, if you read a deep learning paper, it is unlikely that the terms used in those papers can be have already been directly mapped to some esoteric psychology studies. But because active inference has in recent years been developed in a very multidisciplinary manner, this shared language of probabilistic inference is transferable across many different disciplines. Again, to emphasize from the first slide the motivation um, of active inference and why this shared language and interdisciplinary influence is valuable is to understand the connections and patterns among physics, biology, and complex systems in general. And of course, other disciplines are included in this as well. I mentioned psychology, but we can also think about economics or um, genetics and many other subjects. Lastly, active inference explicitly addresses relational and cognitive settings. Um, this means we can ask and potentially even answer questions such as, how do systems act in the face of uncertainty, which can be applied to how we ourselves understand our own actions and how we evaluate our uncertainty and how that can lead to stochasticity in our daily routines, which is related to fields such as cognitive security, as well as higher level societal organizations. How do organizations handle our uncertainty? How is uncertainty at the local level related to uncertainty at the global level? How does the message passing between these two entities work when an entity at one level is the formational block of this higher level entity, which itself can be modeled as a singular thing? And also, what is the relationship between how we form beliefs about the causal structure of our world and how we act within it, which follows from some of the questions I just mentioned. So that would be all for this short introduction. Thank you for your attention. And if you're interested in learning more, I highly encourage you take a look at activeinference.org, at the Active Inference Institute, for more resources on active inference and ongoing discussions, as well as applied research and an overall great community. So thank you and enjoy the rest of your day.